Hey AP Chemistry, I wanted to make a quick correction video on the last minute of my Chapter 3 lecture notes. It was on example 2. I made a very simple calculation error, which is something any of us could do when we're trying to plug and chug and do calculations very quickly, like myself. Even an expert like myself who is so confident in the procedure can quickly overlook small little math errors like this. So in my previous video, what I accidentally did was notice how I had 0.0667 times 1.008 and I got 0.0672, and then I added these two numbers together to get 0.133. Well, I accidentally added 0.6672 to 0.672. I forgot and just quickly did not see that zero because everything's so squished here. So I'm going to rework those problems. Procedure is 100% correct. This is the correct procedure. The answer is not correct. Had this be graded on the AP Chem exam, they'd probably still give you all but maybe 1 credit of point. So if this was worth 4 points, you'd probably get 3 out of 4 points for the one math error that occurred right here. So let me go through it again. So in combustion analysis, we use the products of combustion, which is carbon dioxide and water, to help us figure out an empirical formula. And here's the procedure. You write down the given masses of each combustion product, which would be carbon dioxide and water, convert the masses of carbon dioxide and water to moles. Now remember, to go from grams to moles, grams divided by molar mass is equal to moles. Or I like to do dimensional analysis, so grams times 1 mole over molar mass grams equals moles. Same thing, and you'll see that I did that. Then convert the moles of CO2 to moles of the moles of CO2 and moles of H2O to moles of C and moles of H. For every 1 mole of CO2, there's 1 mole of C. You can see that there's 1 C in there. So if I have 1 CO2, I should have 1 C. For every 1 mole of H2O, I have 2 H's. You can see in there that there are 2 H's for every 1 H2O. And then the extra step is where I messed up on. If the compound contains an element other than C and H, find the mass of the other element by subtracting from the sum of the masses of C and H from the mass of the sample. So I'm going to get the masses of carbon and hydrogen after I get the moles of carbon and hydrogen, moles times molar mass is grams, and then add those together, which is where my calculation error occurred, and then subtract them from the total mass given to me in this example problem, which would be 0.8233. And then write down a pseudo formula, because I'll have to convert those grams back into moles. I'll have moles of everything. I'll write them as small little subscripts, fake subscripts, divide by the smallest subscript, and then make sure the subscripts are in whole numbers. So let's get back to that over here. Okay? So it says, upon combustion, a 0.8233 gram sample of a compound containing only carbon, hydrogen, and oxygen produces 2.445 grams of carbon dioxide and 0.6003 grams of water. Find the empirical formula. All right, so I wrote down that I have 2.445 grams of CO2 and 0.6003 grams of H2O. Great. Now, I convert those grams of CO2 to moles. The molar mass of CO2 is 44, molar mass of H2O is 18, and if you forgot how to do molar masses, you just look on the periodic table for the masses of each of the elements, and add up how many of each element there are in the compound. Carbon's 12, each oxygen is 16, 16 and 16 is 32, plus 12 is 44. All right, so I divide by the molar mass, 2.445 times 1 divided by 44, I get 0.0556 moles of CO2, and then 0.6003 grams of H2O, divided by 18 essentially becomes 0.03335 moles of H2O. Then the next step says convert the moles of CO2 and moles of H2O to moles of C and moles of H. So I have my moles of CO2, 0.0556 moles of CO2. For every 1 mole of CO2, there's 1 mole of CO2. Sorry, there's 1 mole of C. So moles of CO2, moles of CO2, moles of C is left. Or these are equal. Notice how they're equal, because for the same number of CO2s I have are the same number of C's. So those are equal. Now for water, there are twice as many hydrogens as there are water. So 0.03335 moles of H2O times 2 moles of H for every 1 mole of H2O. If I have 1 mole of H2O, I'll have twice as many H's. I have 1 O, but twice as many H's. So I multiply this number by 2. That's how many moles of H I have. And I'm going to use this later in my empirical formula. Now here's the extra step. It says a sample of a compound containing only carbon, hydrogen, and oxygen. I have to figure out how much oxygen I have in this compound. So here's my extra step. I have to convert moles to grams by multiplying by the molar mass. So 0.0556 moles of carbon now. Now these moles are moles of carbon. They're not CO2 anymore because I converted them. They're the same. Right? So 0.0556 moles of carbon times the molar mass of carbon, which is 12 grams per mole. That's on the periodic table. And I get 0.6672 grams of carbon. I think this 667 business tripped me up when I was looking at it very quickly. It can happen to any of us. All right, so 0.6672 grams of carbon. Now I have 0.0667 moles of hydrogen times its molar mass, which is 1.008 grams per mole, and I get 0.0672. And so now I have to add these up, right? Find the mass of the other element by subtracting the sum of the masses of carbon and hydrogen from the mass of the sample. My mass of the sample is 0.8223, and my sum of carbon and hydrogen is 0.6672 grams of carbon plus 0.0672 grams of hydrogen. I should get 0.7344 as opposed to the 0.133 that I got before. So that was a mathematical error on my mistake, my part. Also, how do I know to add these and subtract them? Conservation of matter, right? So really what this step is saying is conservation of matter. The sum of all of the masses of the elements must equal the sum of the compound. If it does not, matter is not conserved, you did something wrong, or there was a problem in the experiment. So we know that this compound has carbon, hydrogen, and oxygen. If I know the amount of carbon and hydrogen, and I know the mass of the whole sample, I can figure out the mass of oxygen. So let's do this math now. I'm going to take 0.8233 grams, which is the mass of the compound that has CH and O, and I'm going to subtract it from 0.7344 grams. That's just the mass of CH. If I subtract CHO from CH, I'll get my mass of O in the compound. So if I do this correctly, I will get 0.8233 minus 0.7344. And I get 0.0889 grams of oxygen are in the compound. Okay? Now, we have to try and get a pseudo formula, right? And I'm kind of going to combine it into these two steps here. We need to get a pseudo formula. I need the moles of each element in the compound. Well, right now I have carbon's moles. It's 0.0556. I have hydrogen's moles. It's 0.0667. Right, that's our moles, that's grams. But our moles of hydrogen are right here. 0.0667, moles of carbon, 0.0556. This is where my mistakes were happening because of those extra zeros. I also got to figure out how many moles of oxygen I have. Well, I know how many grams I have. My grams of oxygen is 0.0889. So now all I got to do is 0.0889 grams times 1 mole of oxygen. For every 16 grams of oxygen, 0.0889 times 1 divided by 16, and I get 0.00556 moles of oxygen. So I'll put that right there. I have 2 zeros there now. All right. I'm going to put 0.00556 there. And then, just like in the procedure with an empirical formula, this is a fake empirical formula. We want whole numbers. You want to divide by the smallest whole number. Between these three numbers, it looks like my oxygen is my smallest. We have 0.0556, 0.0667, and 0.00556. Let me divide everything by 0.00556. 00556. 00556. If I do this math correctly, 0.0556 divided by 00556 becomes 10. If I divide these two correctly, 0.0667 divided by 0.00556, I get 11.99, which that easily rounds to 12. And then if I divide 0.0056 divided by 0.0056, I get 1. And this is the empirical formula for example 2. This is the last example in our lecture notes. This is the correct answer that they have in the textbook. My answer was way off, but notice how I was still trying to do trial and error with that one. I was still trying to figure out, like, okay, I had these moles. My moles of oxygen were completely incorrect because my mass of oxygen was incorrect. You might get a question like this in the future about why was this student's answer incorrect, or if the mass of oxygen is higher, what would happen to the empirical formula? Well, look at this. I would have more oxygens. I'm only supposed to have 1. In my mistake, I got 5. So this is the correct way to do a harder example of combustion analysis. Get your masses, convert them to moles of carbon dioxide and moles of water, because you know how much carbon dioxide and water you have. Then convert those carbon dioxides and waters to carbon and hydrogen respectively. Then if there's any other elements, you have to figure out the mass of that other element by getting the masses of the carbon and hydrogen with this extra step here, subtracting it from the total, and then getting your pseudo formula with the moles of each of them. So don't forget to convert everything back to moles, and then dividing by the smallest moles. This is probably the toughest problem in this chapter. Alrighty, so I'm going to end with that. I apologize for that mistake, but it's a good learning point for us to make sure we be careful to read numbers. Even Mr. T himself can quickly look at numbers because he's so confident in the procedure. Alrighty, if you have any other questions, comments, or concerns, please let me know. I'm available to help if you have any questions with the Chapter 3 exercises.